In order to work with them effectively, we have to be able to calculate the first and second order derivatives of a pair of parametric equations. We need to understand how to do this, what formula we use, and why it comes to be. Now let's imagine we've got a set of parametric equations where we've got x equals x of t, so x is given by some function with respect to t, and y equals y of t, so y is given by some function of t. We've got to determine the first and second order derivatives of this. Now what we're able to do is to determine these making use of the chain rule. So let's imagine I want to do the first order derivative. So let's imagine we want to calculate f dashed of x. Well, we know that that is the equivalent of dy by dx. Now that would be, if y was written as a function in terms of x, I could calculate it. However, y isn't. Y is written in terms of a function of t. So what I'm going to have to do is use the chain rule for this and rewrite it as dy by dt times dt by dx. So I've split it up using the chain rule. So dy by dt, derivative of y, which is a function with respect to t, great. Now I've got to get dt by dx. Well, I don't have a function of t written with respect to x. However, I do have a function of x written with respect to t. And this is where one of our good rules of differentiation comes into play. Because what we can do is rewrite that as dy by dt divided by dx by dt. So what we can do is flip this round, because dt by dx, that's the equivalent of 1 over dx by dt. So I'm then able to change that and say it's dy by dt divided by dx by dt. So I can write it in that format there. So in order to calculate the derivative, f dashed of x, this here is what I use. I use dy by dt divided by dx by dt. Shorthand notation for this is f dashed of x is given by y dashed of t divided by x dashed of t. We also want to be able to do the second derivative of it. Now the second derivative, f double dashed of x, what we're after is d2y by dx squared. So we want the second order derivative of y with respect to x. What I'm able to say is that that's d by dx of dy by dx. So that's the derivative with respect to x of my derivative of y with respect to x. Now, we then have to use the chain rule again. We know dy by dx can be calculated using this rule here. I want the derivative with respect to x of that, but we have to bear in mind that this will still be a function of t. So for my d by dx, what I have to do is I have to write this as d by dt times dt by dx. And again, that can be changed to d by dt divided by dx by dt. So I'm able to use the chain rule again in order to write it in this format here. So if I then go back and substitute that in here, what I'm able to write it as is d by dt of the dy by dx. Remember, that's a function of t, despite it being dy by dx. That's then divided by dx by dt. So what I can then do is think of taking that as d by dt, and I'm going to take dy by dx and write it in this format here. So d by dt of y dashed of t over x dash t. And what I'm then going to do is that's divided by dx by dt, so that's the equivalent of times by 1 over dx by dt. So I'm then going to say that that's times by 1 over x dashed of t. So 1 over the derivative of x with respect to t. So what I now do is to calculate d by dt of this, I use the quotient rule. So we covered the quotient rule previously. What that means is I can then write my second derivative, f double dashed of x, as being equal to the derivative of x times t, x of t, times the second derivative of y of t, take away derivative of y times the second derivative of x, all over the derivative of x with respect to t squared, and that's then going to be multiplied by 1 over the derivative of x. Now, because I've got 1 over the derivative of x and I'm multiplying it through, what I can actually do is make that slightly more straightforward by writing the bottom as a cubic. So overall, I can then write the whole thing as f dashed of x, f double dashed of x, sorry, equals x dashed of t, y double dashed of t, take away y dash t, x double dashed t, all over the derivative of x, so x dashed of t cubed. So there you go, that there is how we calculate the second derivative of a parametric equation when we know x with respect to t and y with respect to t, both as their separate little functions. Now it's easy for me to sit here and show you the formula. What the best way to do to illustrate this is show you a couple of examples. Let's imagine I want to find the first derivative and second derivative of a pair of parametric equations where I tell you that x is equal to 4 plus 4t and y is equal to 3 minus t squared. So for f dashed of x, what I need to remember is that f dashed of x is equal to y dashed of t divided by x dashed of t. Now, because we're going to be working with first and second order derivatives, it's actually useful at this stage to calculate those. So if I've got x equals 4 plus 4t, I know the first order derivative, x dashed, that's going to equal 4. And my second order derivative, f double dashed, is going to equal 0. Similarly, if I look at y, so I know y is equal to 3 minus t squared, so my first derivative, y dashed, is going to be negative 2t. My second derivative, y double dashed, is negative 2. So for the first one here, I need y dash of t over x dash t. So in this case, that means negative 2t over 4. So my derivative f dashed of x is equal to negative a half t. So there you go. That's me got f dashed of t, my first order derivative. Second order derivative, f double dashed of x. What I know is that second order derivative is equal to x dashed y double dash, so first derivative of x times the second derivative of y, take away first derivative of y times the second derivative of x, all over the first derivative, x dashed cubed. Now I've got all the parts here, all I need to do is substitute them in and simplify it and see what I get. So first derivative of x times the second derivative of y, so that's 4 times negative 2, so that gives me negative 8. Take away first derivative of y, negative 2t, times second derivative of x, 0. So that's going to be take away 0. And that's then all going to be over first derivative of x cubed. So first derivative of x is 4. So that's then going to be all over 4 cubed. So what that then gives me is negative 8 over 4 cubed, which is 64. Simplify it down as much as I can, and I get negative 1 over 8. So there you go, that's my second derivative there. Second example I'm going to show you, it's slightly more complex. Given the locus represented by the parametric equations x equals 3 plus 5 cos theta and y equals 4 plus 5 sin theta, first thing I want to do is find the point on the locus corresponding to the parameter value x theta equals pi over 2. Secondly, find the gradient of the tangent at this point. And third, find the concavity at this point. Now remember, when it's talking about gradient, the thing that should instantly jump to mind is the first derivative. When it's talking about concavity, that should be second derivative that jumps to mind. So I've got to answer all of these questions one by one. So first one, find the point on here at theta equals pi over 2, quite simply substitute in pi over 2. So I get x equals 3 plus 5 times cos of pi over 2, and I get y equals 4 plus 5 times sine of pi over 2. Cos of pi over 2 is 0, so 3 plus 0 is 3. Sine of pi over 2 is 1, so I get 4 plus 5, which is 9. So I know then that the coordinate, because remember, that's what it wants is a point is a coordinate, this is just two values, is given by 3, 9. So that's part A. Part B, I want to find the gradient of the tangent at this point. Now remember, gradient means first derivative. So in this case, I know that my first derivative, f dashed, can be given by y dashed over x dashed. So what I need to do is calculate the first order derivative of my x and my y, substitute in the value theta equals pi over 2, and then put all that together in this formula. So, if I know y equals 4 plus 5 sine theta, I know that y dashed is going to equal 5 cos theta. And if I know that x dashed is going to be given by the derivative of this, that's going to equal negative 5 sine theta. What I can now do is substitute in the value theta equals pi over 2 for both of these and see what I get. So theta equals pi over 2, y dashed equals 5 times cos of pi over 2. Well, that's just 0. Negative 5 times sine pi over 2, so it's negative 5 times sine of pi over 2. That's equal to negative 5. So my derivative, f dashed, is going to be given by my derivative of y, so that's equal to 0, over my derivative of x, which is negative 5. Lo and behold, that's equal to 0. Fairly straightforward final calculation for that last bit there. Third part was I had to find the concavity of the curve at this point. So in order to do that, what we have to remember is the formula for my second derivative, f double dashed. Remember that that's given by x dash y double dashed, take away y dash x double dash, over my derivative of x, x dashed, cubed. Now from the previous slide, remember that x dashed, that equals minus 5 sine theta, and my y dash equals 5 cos theta. So if I then take the derivative again, x double dash, that equals minus 5 times cos theta, and my second derivative of y, y double dash, that equals negative 5 sine theta. So what I now need to do is calculate the value of each of these at pi over 2 and then substitute it all in. Well, I know that at pi over 2, x dash was equal to negative 5 times 1, so that was equal to negative 5, and I remember that my y dash at pi over 2 was equal to 0. Second derivative of x is negative 5 times 0, so that's going to be equal to 0. Second derivative of y is going to be negative 5 times 1, so that's going to be negative 5. So if I put all this in the formula, my second derivative, f dashed, is going to be equal to negative 5 times negative 5, take away 0 times 0, so take away 0, all over my first derivative cubed, so negative 5 cubed. So what that's going to do is that's then going to give me 25 over negative 125. And if I take that and I simplify it down, I end up getting negative 1 over 5. So remembering back to when we talked about concavity before, I've got a second derivative, f double dashed, which is less than 0. So I know then that my curve is concave down. So the concavity is concave down. So we've got many applications of this sort of question, and we've got to bring in our knowledge that we've done previously to answer questions which extend and go into this sort of calculation.